In this lab, we were faced with the question of how we can find the concentration of the food dye in 5 different sports drinks. The experiment was conducted so that we could learn how to find the concentration of unknown solutions. In the lab, we were asked to use a spectrophotometer to calculate the percent transmittance of solutions of unknown concentration, and to use that information to find the concentration of 5 sports drinks, each of different color. In the lab, we took 3 different colored solutions, blue, red, and yellow, of known wavelength and concentration. We then put multiple samples of each solution, each of different concentration, into the spectrophotometer and recorded the percent transmittance for each sample. We then made 4 graphs based on our data. Next, we measured the absorbance of 5 different colored sports drinks and used our graphs to calculate the concentration of each one. Here's my graph of percent transmittance versus concentration. As you can see, it steadily decreases but not at a constant rate. Now, what I need to find the concentration of the food dye in the 5 sports drinks is absorbance versus concentration and more of a linear graph. So, I started by converting the percent transmittance into simply just transmittance. So here's my graph of transmittance versus concentration. These two graphs are not very different in the way that they look. However, you can tell that the transmittance versus concentration is a little bit more linear than the other one. I then further transform the transmittance into log of transmittance versus concentration, and now you can see that each different color has a very set linear look to it. Now, based off this graph, there is no way to tell if there's an actual line that goes through these different data points, but we'll get there. Next, I transformed log t into negative log t because absorbance is equal to the negative log of the transmittance. So here's my graph of negative log transmittance versus concentration. As you can see, I now have a positive slope rather than a negative slope. And to prove that these are in fact linear functions, this graph has lines going through each one with equations connected to each line. Now, these data points are not exactly on the line, but these lines represent a basic idea of where these data points would lie. So, now I can use the equation for each of these lines to find the concentration of the dyes in each of the sports drinks. So, here are the final results from my lab. I calculated the concentration and the mass per liters for each sports drink. As you can see, I have that for red, yellow, green, blue, and purple. Green and purple require 2 different food dyes. One thing that's interesting to me is that for every drink requiring blue food dye, the concentration of that dye is something times 10 to the negative 6th, whereas the rest are all times 10 to the negative 5th, thus suggesting that it requires less blue food dye to make a vibrant blue color. Something that concerns me is that the line for the yellow dye is very close to the line for the red dye. Ideally, the line for the yellow dye should be in between the line for the blue dye and the line for the red dye. It is possible that the data for the yellow line, which was gathered by a different group, was marked as if it were for the yellow dye, but really it was for the red dye. The techniques I learned in this lab can be used in the future in situations where I might want to know how much artificial coloring is in my food.